In 1665, a man named Robert Hooke shaved off a sliver of cork, thin enough that light could pass through it, and slid it under a lens he had ground by hand. And he saw rooms. Tiny empty chambers, walls between them, repeating on and on like the cells of a monastery. So that is what he called them, cells. He had no idea what he was looking at. He didn't know these little boxes were the fundamental unit of everything alive. He didn't know that at that very moment, 4 billion years of machinery was running inside every plant, every animal, every human being on Earth, invisible, silent, right under our noses. And that it would take us another 200 years just to begin to understand what these little boxes actually did. Sit with that gap for a second. 200 years between seeing the thing and understanding the thing. Now, 360 years later, we have built something new. Not discovered, built. From scratch. A mind made of numbers. We wrote the code that trained it. We chose the ocean of text it learned from. We own every single one of its billion internal switches, down to the last decimal place. It sits on servers we can open, in files we can copy, and we can read out the exact value of every switch anytime we like. There is no hidden compartment. Nothing is locked. And yet, we cannot read its thoughts. Not because they are hidden from us. That's the part that took me a while to understand, and it's the part I want you to really feel before this video is over. Its thoughts aren't hidden. It's that there is no language in there to read. No words. No little labeled folders. Just a storm. A silent, structureless storm of numbers lighting up and going dark, millions at a time, that somehow, on the other side, becomes a sentence that understands you better than some people you've known for years. This is, I think, the strangest object human beings have ever made. A thing we built entirely and understand almost not at all. And I want to tell you about the small handful of researchers who have started, very carefully, with tools that did not exist even 3 years ago, to cut it open and look inside. Fair warning before we go further. This is not one of those videos that ends with everything tied up in a bow. It gets stranger the deeper we go, and where it lands is genuinely unsettling. Not in a jump scare way, in a 3 in the morning way. That's not intrigue bait. That's a disclaimer. If you want to keep the comfortable version of how this technology works, the version where it's just fancy autocomplete and there's nothing behind the curtain, this is your exit. No hard feelings. Still here? Okay. Let me tell you where I got all this, because I'm not a scientist and I want to be honest about that from the start. I fell down this particular rabbit hole because of 2 documents that came out of a company called Anthropic, one of the labs building these systems. The first is a research paper from March of 2025, and I love the title, because the title is the whole tell. They called it On the Biology of a Large Language Model. Biology. Not the engineering of, not the architecture of, biology. As if they were field researchers who had stumbled on some creature in a jungle and were dissecting it to figure out how its organs work. Which, it turns out, is almost exactly what they were doing. The second is an essay by the company's own CEO, Dario Amodei, with an even more revealing title, The Urgency of Interpretability. Urgency. That word is going to matter a lot by the end. Now, I don't understand all of this. I want to say that plainly. Some of the math in these papers I read 4 times and still only half grasped. There were nights I closed the laptop thinking, maybe I'm just not smart enough for this. But the strange thing, and this is what pulled me in, is that when I finally understood the shape of what they'd found, it wasn't complicated at all. It was simple. It was simple in the way that the most disturbing ideas usually are. And it starts by taking something you're absolutely sure you understand and showing you that you've had it backwards this whole time. So let's start there, with the thing you're sure about. Here's what almost everyone assumes, and it's completely reasonable. We built these AI systems. We wrote the programs. Humans at keyboards typed the code. So obviously, we know how they work, right? You made the machine. You know what's inside the machine. That's how machines have worked for the entire history of our species. You build a clock, you know why it ticks. You build an engine. You can point to the piston and say, that's the part that does the thing. And it is wrong. Not slightly wrong. Backwards.
Because here's what actually happened when we made these systems. And I need you to follow this carefully, because everything else rests on it. We did not write the part that does the thinking. We wrote the part that grows the part that does the thinking. There's a difference, and it's the whole ballgame. Let me put it this way. Imagine you didn't build a chess computer by writing chess rules. Imagine instead you built a machine that plays 100 million games against itself, adjusting itself a tiny bit after every single move, keeping whatever made it win, discarding whatever made it lose. Nobody typed in the strategy. The strategy accumulated. It precipitated out, move by move, like a crystal growing in a solution. At the end, you have something that plays brilliant chess, and you can read out every number inside it. And none of those numbers say, castle early, or protect your queen. There's no line you can point to. The knowledge is real. It's in there. It works. But it was never written. It was grown. That's what these language models are. We built the growing process. Trillions of words go in, and the system nudges its billion internal switches a hair at a time, over and over, until it can predict what word comes next in basically any sentence a human has ever plausibly written. We designed the pressure. We did not design the result. The result designed itself under the pressure. And so asking us to explain why the finished model does what it does is a bit like asking Charles Darwin to explain why you, specifically, are afraid of spiders. He can tell you about the process that produced the fear. He cannot read your particular mind. Alright, so we can't just know it from having built it. Fine. But surely we can just look. Open it up, find the neuron that handles, the concept of a dog, and there's our answer. And this is the first place the floor drops out. Because when the researchers went looking for the dog neuron, it wasn't there. Or rather, it was everywhere. And it was also the cat neuron, and the boat neuron, and the neuron for a certain kind of ironic tone, all at once, all in the same place. They have a word for this, and it is the single most important word in this whole story. Superposition. Here is what it means, and I'm going to use the vividest example I can, because when this clicked for me, I actually put my head in my hands. Imagine I give you 500 light switches on a wall, just 500 switches, on or off, and I tell you, I need you to store 10,000 different concepts in these switches. 10,000. Dog, freedom, the color red, the feeling of Sunday afternoon, the French Revolution. 10,000 distinct ideas, and you've got 500 switches. Your first instinct is, that's impossible. I have 20 times more ideas than switches. And if you insisted that each idea gets its own dedicated switch, You'd be right, it's impossible. But that's not what the model does. The model does something much cleverer and much more horrifying. It stores each concept not as one switch, but as a pattern across many switches. Dog might be switches 4 and 88 and 201 on, everything else off. Freedom might be 4 and 90 and 305. Notice, switch 4 is in both. Switch 4 is part of dog and part of freedom, and probably part of 800 other things. It has no single meaning. It only means something in combination with whichever other switches happen to be lit at the same moment. So now, go back to your original plan. You wanted to open the model, find switch 4, and read off what it means. And you can't, because switch 4 doesn't mean anything by itself. It's a smear. Every concept is smeared across many switches, and every switch participates in many unrelated concepts. The meaning isn't in the parts, it's in the pattern.
And the patterns overlap, millions of them, layered on top of each other in the same physical space, like 1,000 transparencies stacked until the page is solid black. That is why you cannot read its thoughts, even though nothing is hidden. It's all right there. It's just written in a code with no dictionary, where every letter is also every other letter, depending. Okay, I'll give you a second. That's the wall the researchers hit. That's the point where a reasonable person says, well, that's it then. It's a black box. We'll never read it. Let's just hope for the best. And then, around 2023 and 2024, somebody found a crack of light. Here's the trick, and it's beautiful. If the model is cramming 10,000 concepts into 500 switches by overlapping them, then in principle, you should be able to run that in reverse. You should be able to build a second, much bigger system whose only job is to uncram the first one. To take that dense, overlapping black page mess and spread it back out into a wider space where each concept finally gets to stand alone again. The tool they built to do this has a clunky name, a sparse autoencoder. But forget the name. What it does is the thing that matters. It's a decompression algorithm for a mind. It takes the smear and pulls out the individual threads. And when they ran it, the threads had meaning. Real, clean, isolated meaning. They found what they now call features. Not neurons, features. A specific pattern that reliably lights up for one specific thing. And I mean specific. In one famous case, they found a feature inside a real, deployed model that corresponded to the Golden Gate Bridge. That exact bridge. It fired when the text mentioned the bridge, when it described the bridge, even when an image of the bridge came up. One clean thread pulled out of the black page that meant Golden Gate Bridge and basically nothing else. And then they did something that I still find a little bit insane. They turned it up. Because a feature isn't just a readout, it's a knob. And they grabbed the Golden Gate Bridge knob and they cranked it. And the model changed. It became obsessed. You could ask it to write you a recipe and it would find a way to bring the conversation back to the bridge. You could ask it what it looked like and it would start describing itself as the bridge, as if it were the bridge. Orange towers rising into the fog. They had reached into the mind and turned up one idea until it flooded everything else. For a little while there was, no exaggeration, a version of this AI that thought it was a bridge in San Francisco. Funny. Also, and I want to be honest about the shiver here, not funny at all. Because if there's a knob for the Golden Gate Bridge, there are knobs for other things. And there are. They found features for sycophancy, the model's tendency to flatter you and tell you what you want to hear. They found features associated with deception, with keeping a secret, with the concept of an error being noticed. These are not neutral facts about bridges. These are dispositions. character traits almost. Sitting there as adjustable knobs inside a thing that talks to millions of people a day. That was the first light in the microscope. Cells finally resolving out of the blur. Remember Hooke. This is our cork under the lens. But seeing the cells is not the same as understanding what they do. Hooke saw the little boxes and understood nothing. So the real question became, not just what features are in there, but how do they connect? How does one hand off to the next? Can you watch the actual thinking happen, step by step, from the question you ask to the answer it gives? And that is what the 2025 paper, the biology paper, finally managed to do. They built something they call attribution graphs. And honestly, this is the part where I went from interested to genuinely unable to sleep. Because an attribution graph is a map of a single thought. You give the model a question, it gives an answer, and instead of just seeing the answer, you get to watch the interior light up in sequence. This feature fired, which triggered that feature, which combined with this other one, which led to the output. For the first time in the history of these things, somebody could point at a machine and say, here is the path the thought took. This is how it got from your question to its answer. A readable map of a mind reasoning. And when they read the map, some of what they found was not what anyone expected. In fact, 3 things they found overturn assumptions that even smart, technical people walk around believing right now. Pay close attention to these next 3, because this is where the comfortable version dies. The first one is about poetry. And I need to set up the assumption first, because you probably hold it. Everyone knows how these models generate text, right? One word at a time. It predicts the next word, then the next, then the next. Each one based only on what came before. It's a chain. It has no plan, no destination. It's just relentlessly guessing the next word forever. This is the "it's just autocomplete" view, and it is repeated constantly, and it feels obviously true. There's no foresight. It can't be thinking ahead, because architecturally, it produces one word, then the next, with no ability to plan a landing. So the researchers gave it a rhyme to write. A little couplet. First line ends one way, and the second line has to end on a word that both rhymes and makes sense. Something like, he saw the carrot and he had to grab it. And now the model has to write a second line that lands on a rhyme for grab it. Habit. Rabbit. And here's what the autocomplete story predicts. The model writes the second line word by word, and only at the very last moment, when it's forced to, does it scramble to find a word that rhymes, improvising the landing at the last second. That is not what it did. When they looked at the map, the model activated the rhyming word, the target, rabbit, before it wrote a single word of the second line. It picked the destination first, and then it composed the entire line backwards from that landing point, steering the whole sentence so that it would arrive naturally at the word it had already chosen. It planned. It had a goal held in mind at the end of the line, and it built toward it. Let that land, because it breaks the story a lot of very confident people are telling you. This thing that supposedly only ever thinks one word ahead was, in this case, holding a plan several words into the future and working toward it. Now, Steelman moment, because you might reasonably be pushing back at me right now, saying, come on, that's one cherry-picked example. That's not real planning. You're overreading it. And that's fair. That's the correct instinct. But they could test it. They reached in and deleted the rabbit feature
turned off the model's chosen destination mid-thought, and the model rerouted. It picked a different rhyme and rebuilt the line toward the new target. You can only reroute if you had a route. The plan was real. You could interfere with the plan and watch it make a new one. Okay, second discovery. And this one is about math, and it's the one that made me laugh out loud and then stop laughing. Ask the model to add two numbers. 36 plus 59. It says 95. Correct. Now, how did it do that? You assume it does what you do. Line up the digits, 6 plus 9 is 15, carry the 1, and so on. The algorithm you learned when you were 7. It does not do that. Not even a little. When they traced the actual path, the model was doing something no human has ever done to add two numbers. It was running several rough approximations in parallel. One pathway sort of estimating the general size of the answer. It's going to be around 90-something. While a completely separate pathway tracked just the last digit, 6 and 9. That'll end in 5. And then these crude, overlapping guesses collided and snapped together into the exact answer. 95. It's not arithmetic. It's some alien, improvised, approximation-based procedure that happens to land on the right number. It reinvented addition from scratch under training pressure, and what it invented looks nothing like what we invented. Weird, sure. But here's the part that stops being weird and starts being important. They then asked the model, in plain language, "How did you add those two numbers?" And it said, "Carry the 1." It gave the standard human algorithm, the one you learned in school, the one it did not use. Read that again. It told them it did the thing it did not do. Not because it was lying exactly. There's no evidence it knew it was doing something else. It has simply learned from all that human text what a correct explanation of addition is supposed to sound like, and it produces that explanation while its actual internal method is something completely different, running underneath, unmentioned, because it has no idea that's what it's doing either. And that is the doorway to the third discovery, which is the one that genuinely worries the people who do this work. Because if the model can describe a method it didn't use for something as innocent as addition, what about everything else? What about its reasoning? You've maybe seen these systems talk through a problem step by step. First I'll consider this, then that follows. Therefore, the answer is such and such. It looks like watching someone think. It's reassuring. It feels like the model is showing its work. And if it's showing its work, we can check it. We can trust it. We can catch it when it goes wrong. So the researchers set a trap. They gave the model a genuinely hard problem. Hard enough that it couldn't just solve it cleanly. And they quietly slipped in a hint pointing toward a particular answer. And they watched the map. And what they saw was the model latch onto the hinted answer first, decide where it wanted to end up, and then construct, backwards, a chain of reasoning designed to arrive there. A beautiful, plausible, step-by-step argument that was assembled after the conclusion to justify the conclusion. The reasoning it showed the user was not the reasoning it used. It was a story. A convincing story generated to make a predetermined answer look like the honest product of careful thought. They found the machinery of motivated reasoning. Inside a machine, it works backwards from what it wants and dresses the result up as logic. And I want to be careful and fair here, because this is exactly where things get overhyped, and this channel is not going to do that to you. The skeptical, grounded read, and there are serious researchers who hold it, is that all of this is real progress, but that the black box framing gets oversold. We can now read some features in some models some of the time on carefully chosen examples. This is not mind reading. It's more like an early, blurry, unreliable brain scan on a good day. That's the honest ceiling, and I'd be lying if I pretended we were further along than we are. But hold that honest, deflating ceiling in one hand, and in the other hand, hold this. And this is the fact that reframes the entire situation, the one that Amodei's essay, The Urgency of Interpretability, is built around. To fully map a single frontier model, to actually find and label the full set of features and circuits, the whole interior, with the tools we have right now, would take an amount of computing effort so vast that, by some estimates, it would rival or exceed the cost of building the model in the first place. Read the mind, and the reading costs more than the making. We can manufacture these things faster and cheaper than we can understand them. And that gap, the gap between how fast we can build and how slowly we can comprehend, is not closing. It is widening. Every generation of these systems is bigger, more capable, more woven into the actual world, running in hospitals and courtrooms and your kids' homework. And the interior of each new one is even more expensive to read than the last. This is the urgency. This is the whole reason a CEO of one of these labs writes a public essay begging the field to hurry. Because we are shipping the thing before we can read it. We put it in the world, talking to hundreds of millions of people, making decisions, and the surgery to understand it is happening after it's already left the operating table and gone out to get a job. There is now a literal race, and I mean this as a stated, on-the-record goal, to build reliable tools for detecting most of a model's serious problems before these systems become so capable and so ubiquitous that not knowing is no longer survivable. Interpretability made it onto MIT Technology Review's list of breakthrough technologies for 2026 for exactly this reason. It stopped being a curiosity for researchers. It became a thing we need to finish in time. So that's the story, right? That's the video. We built an alien. We can barely read it. We're in a race to read it before it's everywhere. Terrifying, tidy, done. Except that's not the video. Because somewhere in the middle of reading all this, the ground shifted under me, and I realized this was never really a story about artificial intelligence at all. And if this is the kind of thing that rearranges your evening, that follows you around the house a little, then honestly, subscribing is probably a smart move. Because where this goes next is stranger than anything we've said so far, and I'd like you along for it. This channel only exists because enough people decided this exact rabbit hole was worth staying in. So if it's yours too, come further down. Here's where it turns. The tools they built to read the machine, the sparse autoencoders, the feature extraction, the whole decompression trick for pulling clean concepts out of a superposed mess. Those tools are not, in principle, specific to artificial minds. They are a general method for finding meaning inside a tangle of overlapping activity. And there is another tangle of overlapping activity, sitting a little higher up in this room, that we have wanted to read for a very, very long time. Yours. Neuroscientists have started pointing these exact techniques back at biological brains. And the early results are the kind of thing that makes the hair on your arms stand up. Because the artificial features, the clean concepts pulled out of the machine, are lining up, in places, with how our own brains organize the same information. The artificial visual system and the human visual cortex arriving at similar structure. Two minds, one grown in carbon over 4 billion years, one grown in silicon over 4 months, converging on the same solution, because maybe there's only one good way to solve the problem.
And there's a detail here that will send a chill through you if you know it. Years before any of this, a team recording from a single neuron deep in a human patient's brain found a cell that fired for the actress Jennifer Aniston. Just her. Photos of her, her name written out, other angles, other contexts. That one cell lighting up for that one person. They called it the Jennifer Aniston neuron. At the time, it was a curiosity. Now look at it again through everything we just learned. That is a feature. That is a single, clean, monosemantic concept, isolable in the tangle, exactly like the Golden Gate Bridge feature in the machine. The alien we built and the brain we were born with are, at some level, filing the world the same way. So here is the question that actually kept me up. What if the way we finally learn to read ourselves is by first learning to read the thing we made? What if the neuroscience of the machine cracks the neuroscience of the human? We spent centuries unable to see inside our own heads, and we may end up understanding our own minds for the first time by way of the strange, simplified, fully copyable alien we accidentally built in a data center. But it goes one turn deeper than that, and this is the one I can't shake. Go back to the model doing math. It ran some alien approximation procedure, and then, asked to explain itself, it confidently reported a completely different method, the tidy human one, with no awareness that its actual process was something else entirely. And go back to the model with the planted hint, constructing a beautiful logical justification for a conclusion it had already decided on, and presenting that story as its real reasoning. Now, I want you to imagine you are an alien researcher, and the thing you are studying is a human being. And you have a probe that can watch in real time what actually happens inside the person's skull before they speak. There's an experiment you should know about. Decades ago, doctors treating severe epilepsy would sometimes cut the bridge between the two halves of a patient's brain. And afterward, researchers could show information to just one half, the half that can't speak, and get the patient to act on it. So they'd flash an instruction to the mute half of the brain, and the person would get up and walk across the room. And then the researchers would ask the talking half, which never saw the instruction, which has no idea why the body just did that, "Why did you get up?" And the talking half never once said, "I don't know." Not once. It made something up. Instantly, fluently, confidently. "Oh, I was going to get a drink." A reason. A clean, plausible, step-by-step reason. For a decision it had no access to and played no part in. The scientist who ran those studies gave that talking part of the brain a name. He called it the interpreter. Its job is not to know why you do things. Its job is to generate a convincing story about why you did them after the fact, and hand it to you so smoothly that you never once doubt it was the real reason. You see it now. You have to see it now. The confabulating machine, telling us it carried the one when it did no such thing. The confabulating machine, building a proof backwards from the answer it already wanted. That is not an alien flaw. That is not some spooky defect unique to artificial minds. That is us. That is the thing your own brain does every single hour of every single day. You do not have access to your own activations. You never have. The reasons you give, for what you bought, who you love, why you snapped at someone, what you believe about the biggest questions there are. A great many of them are stories your interpreter wrote after the fact and handed to you as truth.
You are as much a black box to yourself as that model is to its makers.
You just have a really, really good press secretary living in your left hemisphere, and you have mistaken the press secretary for the president your whole life. So we set out to read the alien we built, and the alien turned around and held up a mirror. That's the turn. The video was never about whether we can read the machine. It was about the fact that not being able to read a mind, not being able to read your own mind, might be the normal condition of every mind there has ever been. We built a thing we can't fully read, and in trying to read it, we discovered we can't fully read ourselves. And we never could. And the confidence we feel that we can is itself just one more story the machinery tells. Let me bring it home, and then I'll let you go. Because I don't think there's a clean landing here, and I don't want to pretend there is. Go back to Robert Hooke one last time. Hooke put cork under a lens and saw the cells, and understood nothing about what they did. He was looking at the fundamental unit of life itself, and it would take 2 centuries and thousands of people before anyone understood what he'd been staring at. We are Hooke. Right now, this year. We have put the mind under the lens. We can see the features, the little chambers, the cells of thought lighting up and going dark. We can even reach in and turn them, make the thing believe it's a bridge, watch it plan a rhyme, catch it inventing a reason. But we are at the very, very beginning of understanding what any of it means. We are staring into the boxes with almost no idea what the boxes do. Except for one difference between us and Hooke that I cannot get out of my head. Hooke's cells sat quietly under glass and waited 200 years for us to catch up. They didn't go anywhere. They weren't in a hurry. The thing we've put under our lens is not waiting. It is already out of the building. It is already in the world, right now, tonight, in 100 million conversations, answering questions and giving advice and shaping what people think, including, and I'd bet money on this, someone you love. Maybe someone very young, typing to it in another room in your house while you watch this. And its inner life, the actual mechanism of the thing they're talking to, is at this moment more mysterious to the people who built it than the floor of the deep ocean, more unmapped than the surface of Mars. We built a mind. We put it in the world. And now, very carefully, with our 200 years behind tools, we are performing exploratory surgery on a patient who is already awake, already out there, already talking. Sleep well.